Hello, welcome to the best little lab in physics. Today we're going to talk about why binary mechanics is the best theory of everything available to the physics community in the world today. We start with a model of space, which involves a lattice of spot cubes as shown here that we've talked about in previous videos. Some might prefer to say that space contains a lattice of these spot cubes. So let's look at what happens when we make that assumption. We get an absolute reference frame defined. Let's review that. In physics, a reference frame is a set of coordinates used to determine properties like position and velocity. A frame of reference, or reference frame, is an absolute coordinate system whose origin, orientation, and scale have been specified in physical space. An absolute frame of reference is some fixed reference frame that every observer in the universe would agree is at rest at all times. In contrast, for example, in Newtonian physics, an object may be at rest in one reference frame, but moving in another. And Newtonian physics uses the Galilean reference frame idea. If this is true, it means that there is no absolute way to determine if an object is in motion or not, or what its velocity in fact is, in some more definite sense. And in fact, we couldn't even know what the ground states of particles are when they have zero motion. With full quantization and primary length constant L, binary mechanics defines an absolute reference frame. The binary mechanics absolute reference frame enables study of, first, the composition and properties of objects, such as electrons and protons with zero motion, which occurs at 0 Kelvin temperature. Secondly, absolute linear and angular momentum of any object or observer. Note that a reference frame is a perspective that one uses to determine if an object is in fact moving. So binary mechanics provides you with additional capabilities to study particles, what their ground state is, what their motion in fact is, and what is involved in having observable motion of a particle. Cosmology modeling must be based on a successful TOE, or theory of everything. First, unsuccessful TOEs and cosmologies require input parameters based on unexplained measurements, such as the velocity of light c, the elementary electric charge E, Planck's constant h, the mass of the electron and proton, etc. Considering hundreds of proposed TOEs, only binary mechanics has derived the measured values of so-called fundamental constants. Here is the constants derivation tree. Binary mechanics quantizes energy, space, and time. Okay, put on your scuba mask because we're going to take a deep dive here. If you postulate that energy, space, and time are quantized, the next logical question is what values do they have? Say, in energy in kilograms, length in meters, and time in seconds. What values do they have? Binary mechanics takes a number of measurements in physics and has derived all of these values based upon these three, what I call primary constants. What are those values that we've derived? Electron electric dipole moment, which equals 0. Proton electric dipole moment, which is greater than 0. The coupling constant alpha, electron rest mass, all of these items in the red boxes. Vacuum light speed, Planck's constant h, which relates, of course, to the intrinsic electron and proton spin, elementary charge E, as well as intrinsic electron magnetic moment. To summarize, the values in the red boxes shown in this slide are all unexplained measurements. And that is what conventional physics is trying to tell us. They don't know why those measurements, the specific numerical values obtained, say for Planck's constant, actually have the values that are measured and observed. Binary mechanics turns the table upside down and says, our postulates can be used to actually derive these values in the red boxes, which I now call secondary constants, because these three values are the primary constant. This is a major revolution in physics thinking. No other laboratory has done this. Okay, let's consider a second point in why binary mechanics is a successful theory of everything. Incomplete TOEs and cosmologies lack a useful model of motion mechanisms. Descriptions of motion, such as Newton's mechanics, are an important first step. However, motion descriptions are not equivalent to knowledge of motion mechanisms. Think about that. Example, velocity, acceleration, torque, etc. describe motion, but not how it occurs. Binary mechanics has provided the best understanding to date of how things move. Here's our elementary particle flux and motion tree, where we start with simple elemental events to get to more complex phenomena such as particle motion. We have the discovery of lepton-quark transition, where elements of the electron spot in the spot cube that I showed you at the beginning can exchange quanta with the right-handed d quarks, which are parts of protons. And the positron, which is the right-handed electron, with the left-handed d quarks. And so these two kinds of exchanges are lepton-quark exchanges. Further, we have quark and anti-quark transitions which are possible, which means that individual one states, or what I call quanta, can exchange between the right-handed d quark spots and the left-handed d quark spots. These elemental particle fluxes can then give us mechanisms of lepton and proton motion. If we just string the items together, shown above, lepton motion mechanism can be determined. In other words, for an electron to move, that's our left-handed electron spot, quanta must pass through the right-handed d quarks to get to the next electron spot. So this would be quark-mediated electron motion. Likewise, the positron particle needs to move through the antimatter left-handed d quarks in order to arrive at the next positron spot in our Spatol lattice of spot cubes. Next, we have the discovery of lepton-mediated proton motion, where the above transitions are stringed together for lepton-mediated proton motion. Finally, there's the quark-antiquark mechanism of proton motion, where the antimatter d quarks can directly exchange one-state quanta with the right-handed and vice versa.